sometimes there's
No,
interference.
this one is no. The
Oh,
only
this is
one
some
piece.
fancy. Okay, thank you.
Yes. So okay, we can start probably. So, okay. So it's a great pleasure to introduce Mohit, Professor Mohit Randeria, so whom I have known for, I think, for many years, very long time. So he's currently a professor at Ohio State University, and his focus is on quantum materials, condensed matter theory, and like diverse areas within these topics. So he obtained his BTech from IIT Delhi, then MS from Caltech, and then PhD from Cornell. So after a postdoc in Urbana-Champaign, so he taught in Stony Brook, Argonne National Lab, and then he was at TIFR for almost 10 years. This is when I actually known him. I've also, I think, attended some course by him. I think I took a reading course with him or something like that. Yeah. So he has held various visiting professorship in Urbana-Champaign, Berkeley, MIT, Harvard, and I think he has also, I mean, he's a winner of many awards, I mean, even from India, like Bhatnagar Award, ICTP Prize, IIT Delhi Distinguished Alumni Award, I think Swarnar Jayanti Fellowship, and many others. So he's a fellow of American Physical Society, American Association of Advancement of Sciences, and recently he has also won this John Bardeen Prize in 2022 for his work on superconductivity. So he is currently visiting IISc till end of April as a Infosys visiting professor, so hopefully we'll see him more. And I think with this, without further ado, I'd like to invite Professor Randeria for delivering his talk.
Thank you. So, thank you very much. I really appreciate the invitation from many colleagues here, Saptarshi, Sanyukta, Sanjeev, all of them welcome me here, so I'm very grateful to them. I also realize that I work on a part of physics which is not much represented here, so I will try to keep my talk accessible to a general audience, and please feel free to interrupt me whenever you feel that I'm saying something which is not easy to understand. So I would like to really acknowledge the hospitality of the Indian Institute of Science, Bangalore, because it's because of them that I've been able to visit here. So let's start with superconductivity. So this is actually Kamerlin Owens' original data, where he saw that the resistance of a sample of mercury went to 0 precisely below about 4.2 Kelvin. It was some years later that Meister and Ostenfeld showed that not just transport properties, but even in thermodynamic properties, this class of materials showed something really strange. Namely, not only was the resistance 0, but if you put a magnetic field about Tc and you cool below this transition temperature where you lost resistance, the field was expelled, at least insofar as the fields were small. So B inside is also 0. Actually, this was a huge puzzle on which a very large number of great physicists tried to work. And for 45 years, there was no theoretical understanding of what was going on. So it took literally more than 45 years after 1911 to solve this problem, to the extent that people had said that all theories of superconductivity are wrong, or it's a failure of our imagination. I'm quoting Feynman when he said that. And then in 1956 and 57, Bardeen, Cooper, and Schrieffer came up with the theory of superconductivity at that time. And they showed that this is a sort of macroscopic manifestation of quantum mechanics. And that's responsible for this remarkable set of observations. And this led to the second Nobel Prize for Bardeen, the only winner of 2 Nobel Prizes in physics. The first one was for the discovery of the semiconductor transistor. I'll have more to say about BCS theory. But actually, this field of superconductivity has a diverse impacts in all areas of physics. Okay, so Nambu got the idea of spontaneous symmetry breaking in particle physics. He brought it from superconductivity, or the idea of the what is now called the Anderson-Higgs mechanism also came originally from the theory of superconductivity, and I'll show you the original papers. Then Ginzburg and Landau developed the Ginzburg-Landau theory of superconductivity, which had huge implications beyond superconductivity to critical phenomena in effective field theory, where people talk about the Ginzburg-Landau-Wilson approach to critical phenomena, to liquid crystals and soft matter physics, where Dejean adapted all the things from Ginzburg-Landau theory. This was the first place where topological excitations in condensed matter played a center role. Not quite true. Dislocations in solids were known for a long time, but this is a different kind of things. So Abrikosov predicted vortices in type 2 superconductivity, and Berezinski and Koslitz-Thouless predicted how vortex-anti-vortex binding in 2 dimensions plays a role. It led to the development of new tools like tunneling spectroscopy, for which Giaver won the Nobel Prize, the Josephson effect, for which Josephson won the Nobel Prize. Okay, it led to the understanding of superfluidity in helium-3. Actually, most of the people on this list, there'll be 1 or 2 people who have not won Nobel Prizes, by the way. Okay, ultra-cold atomic gases, which led to the study of the BCS-BEC crossover, or even in nuclear physics, like pairing in nuclei, superfluidity, neutron stars, or color superconductivity QCD. So this area of superconductivity has had diverse impacts across physics. So here is Nambu's first paper, Nambu and Honolosino, dynamical model of elementary particles based on an analogy with superconductivity, paper 1 and paper 2. Okay, this is what led to his work. Actually, Nambu wrote a very beautiful paper on superconductivity itself also. Here is Higgs's paper, okay, where this is the first paragraph of Higgs's paper, and he says, the phenomena, meaning the Higgs effect, is just the relativistic analog of the plasmon phenomena to which Phil Anderson has drawn attention, that the scalar zero mass excitations of a superconducting neutral Fermi gas become longitudinal plasmons of finite mass when the gas is charged. Okay? And the beauty of this is that not only did superconductivity play a huge role in the theory of the Higgs particle, but superconducting magnets were used in a very essential way in the experiment that detected the Higgs particle many, many decades later as well. Okay. So that's in physics. Many of us have relatives who ask us, whatever you do, what is it good for? Okay. So here's a good example. Every MRI machine in every hospital in the world, at least the good ones, all use superconducting magnets. Okay. They use niobium titanium or niobium tin. That's current day technology. Looking at possibly very important technologies, you'll see that very recently people have made small tokamaks for magnetic confinement for fusion using high temperature superconducting magnets. We have to see where this technology goes, but there are startup companies that are claiming to make money for their investors. Okay. And there are huge companies like Google and IBM which are using Josephson junctions for making superconducting qubits. Okay. So of course, right now we do not know what platform will ultimately be the winner for doing sort of quantum computing and information processing, but superconducting qubits using the Josephson junctions is certainly one of the most shall we say, promising ones at the present time. There are others as well. Okay, so that's a reason why people who are not interested in superconductivity also should be, at least at a colloquium level, be interested in superconductivity. Okay, so now let's discuss which materials show superconductivity and what their transition temperatures are. So if you look up the periodic table, then everything which is colored actually is a superconductor. The blues are at ambient pressure, the greens under high pressure. And these are just the elements, okay? Then there are a whole host of compounds, okay? So I've marked the high temperature copper oxide materials, yttrium, barium, copper oxide is one of them, but there are many others as well. Okay, and this periodic table is also wrong because a few years ago it was shown that carbon, which was shown to be non-superconducting in this database, is actually superconducting if you just take two sheets of graphite and twist them to the right angle, okay? The correct magic angle. I didn't mean right angle in the sense of 90 degrees. It's a 1 degree angle. Okay, so there it is. There's an abundance of elements, compounds, and alloys in nature which show this behavior. And then you can ask, and below what temperature do they show this behavior? And one way you can plot it is to say critical temperature, the temperature below which the system goes superconducting, versus the year in which it was discovered. So this is, let's see, this is Camerlenons. And this is 1986, December, the cuprates are discovered. One important lesson for me here was that I was just finishing my PhD that December when this was discovered, and I was not taught superconductivity in graduate school because my professor said that this is a dead field. Everything that was to be known about this field is known. BCS have spoken the last word, so don't bother and waste your time on that. So to the young people in the background, listen to your professors, but not always, okay? Okay, okay, good. So then, boom, TC jumps up above the liquid nitrogen temperature. So that's the copper age. And then there was the iron age. And now we have entered the hydrogen age. And of course, there have been a lot of fraudulent claims also, unfortunately, in the hydrogen age. But there are some real claims which everyone accepts. So we have superconductors that are superconducting at 250 Kelvin, which is pretty close to room temperature. However, I don't think a lot of experiments have been done, or there's a lot of excitement about them, because they have to be made at ultra high pressures, 170 GPa, and also kept at ultra high pressures. So just to give you an idea of what this pressure is, the pressure at the core of the Earth is about double of that. Okay, so it's very high pressure. Now, this would seem to suggest that with time, TC just marches on. You just wait and it'll keep on going up, and maybe that's true. In fact, if you ask nuclear physicists and astrophysicists, then they say that the estimated TC for the superfluidity of paired neutrons in neutron stars is 10 to the power 9 Kelvin. Okay? And I'll leave the astrophysicists in the audience if there are any to discuss how we know that from pulsar glitches and so on. That's really outside my expertise. But then all other scales in this highly compressed state of matter are very different. The Fermi energies are 100 mega electron volts. So this is a small number compared to that. Yes?
The 10 to the 9 prediction is from BCS theory or something?
Okay, I'm not going to say it's an estimate, it's a prediction. I don't know, but it is what it is. Okay, you can look at the literature on that. But it's some huge number. Okay, because actually it's estimated, by the way, that the temperature of those pulsars is itself 10 to the power 8 Kelvin. Okay, so there. Okay, so a better way to plot this is not versus time, but versus some other scale, so that we have some dimensionless object we can think about. So this is what is called the so-called Uemura plot, and of course every physicist knows that you can hide a lot of sins in a log-log plot, but it's good also to communicate a lot of data. Okay, so this is the log of the critical temperature, which is a measured quantity. This is the log of the Fermi temperature, which really is quite ambiguous when you come to strongly correlated multi-band systems, with some number which we can give or take a few estimate. And this suggests that there seems to be some upper bound on TC, that there are absolutely no materials over here. Now, is that really true? And if so, why? Okay. Secondly, the bound cannot depend on the mechanism of superconductivity, because if you ask which are the superconductors which come closest to saturating this bound, they're magic angle twisted bilayer graphene, two ultra cold atoms, Fermi gases, and monolayer iron selenide on STO. They have nothing in common other than the fact that they're all paired superconductors. Okay? So you might say, oh, but why are you pointing to this? What about over here? So over here, people don't show materials because there are many, many which are very well understood within BCS theory. So that's not exciting, but there are lots of materials over here. Okay? It's this part which is interesting. So that's what got us started. And actually, as I will try to show you, we have succeeded in deriving exact bounds in two-dimensional materials. The bounds will not in general be in terms of EF, so we will discuss that as well. And at the very end, I will show you why, despite the success that we've had in 2 dimensions, the question of bounding TC in 3 dimensions is still an open question, despite the fact that many of the systems here are in fact 3-dimensional. But many are 2-dimensional. This is 2-dimensional, that's 2-dimensional, and there are 2-dimensional versions of this too. So we'll discuss that. Okay, so that then raises the question, what determines the transition temperature? You know, how do we begin to say that? Yes. Yes.
So in the previous one,
Do you take into account that pressure as a separate parameter, or?
No, you can just write down what it is. You just take whatever it is.
No, because this you gave some example that extreme high pressure there.
Yeah, you can put that material here and it will be down here below this line.
Okay, below
Yeah,
that.
it will definitely be below this line.
I see. Thanks.
Okay, very good. So let's do a very quick review of what you would learn in some class. Okay, so a metal is a filled Fermi sea with gapless excitations on the Fermi surface. And Kf is the radius of this Fermi surface, and epsilon Fermi is the Fermi energy, or you can call it the Fermi temperature. Everyone knows that. What BCS showed was that if you put a weak attraction between electrons, and weak seemed reasonable because electrons are repulsive, you know, because they have a Coulomb interaction, you have to have some other mechanism. BCS talked about electron-phonon interactions, but it could be anything else as well. Then that weak attraction would lead to a gap in the spectrum because you form Cooper pairs, and this is the binding energy of the Cooper pairs. So you no longer have the Fermi surface, you destroy it. So in fact, there's a phase transition at TC at which 2 different phenomena occur simultaneously. First, the pairing of electrons, and that gives rise to the binding energy of pairs, the superconducting gap. Second, once you pair these electrons, you get a macroscopic condensate of pairs, and that leads to all the super properties, like super fluidity, meaning zero resistance flow, or Meissner effect, and so on, coming from this condensation. So in this picture, basically TC just scales with the gap, because the stronger the gap, the more strongly you pair the electrons, and the higher the temperature you have to go to destroy the pairing. Okay, these 2 things just scale together. And this is true even in more elaborate theories of electron-phonon interactions. But this would suggest that the stronger the attraction, the higher the TC. But is this true? Or is there some other quantum mechanical phenomena that just simply limits the growth of TC? So here's what I said. For many, many materials that are very well understood in terms of BCS mean field theory, pairing is fragile because you can just barely bind the pairs. But the condensate is very robust so long as the pairs exist. So TC is just related to the binding of pairs. But for many of the relatively less understood superconductors, this is completely flipped. Pairing seems to be robust, but the condensate is very fragile. In that case, TC is not determined by the binding energy of the pairs, but it's determined by something which we call the stiffness, which controls the fluctuations of the phase of the condensate. This will be a big player in the remaining part of the talk, and I will explain it in much more detail, okay? So it's not just words that I want to flash with you. One way of thinking about this dichotomy is the following. You see, superconductivity has an order parameter, which is a complex number. The complex number has an amplitude and a phase. So locally, that's the order parameter. How can you kill long-range order? One is you just kill the amplitude. That's BCS theory. But the other is the amplitude is robust because pairing is robust, but the phase is floppy, and so there's no long-range order in the phase, and that's how you kill superconductivity. And randomize.
Now, like your Fermi energy basically goes, right? Or I mean, like
So
you are
the
not
Fermi surface is destroyed. There is still an energy
Yeah.
scale, but there's a gap opening up on the Fermi surface.
So you can still talk about, like in the previous one, you are plotting as a Fermi temperature versus the.
So temperature, you know, you tell me the density, I'll tell you, and mass of the particle, I'll tell you
I'll
the
tell-
Fermi
okay.
energy. That will define the Fermi temperature.
Okay, so
But there is no Fermi surface of gapless excitations.
Okay.
That's what I'm saying. Yeah? The energy is still a scale. You can write it down.
Yeah.
The stiffness is very small. So there are a lot of soft matter people here, you know. Order is not just defined in terms of some correlation function showing long range order. Order is defined in terms of if I kick it, how it responds, you know, stiffness, right? That's what happens in elasticity theory, right? So here also you can ask, what is the free energy for bending the phase of a superconductor? And that is the stiffness. Now that's a very theorist way of discussing it. But what is the stiffness for an experimentalist? How, in solids, this would be the elastic modulus. But what is the analogous stiffness in superconductivity? And the answer is there are very simple ways of measuring it. So I said that fields are suppressed inside, magnetic fields are killed inside a superconductor. That happens on the scale of this London penetration depth, the Meissner effect. And it turns out, I mean, take me too long to show it, that the London penetration depth is directly related to the stiffness. Okay, so it's so this is just the permittivity of magnetic permeability of vacuum, E, H, so on. Another way to talk about it is if you measure the optical conductivity of any superconductor, okay, then you expect that in DC there's going to be an infinite conductivity. Actually, it turns out that infinite conductivity is a delta function, okay? And the weight of that delta function up to universal constants is just the stiffness. So there are ways of measuring it. Now you would say, how can I ever measure a delta function in an experiment? Okay? The answer is you can't measure the real part of the optical conductivity, which is absorption, and get a delta function. You can get the rest of the curve. But you can measure the imaginary part of this. And the delta function in chromastonic will give you a 1 over omega. And that you can measure in the lab, and you can learn about the stiffness. So the stiffness is very much an observable quantity. And theoretically, it's related to the how the energy cost of bending the condensate. Yes?
So in the other case where you have the amplitude fluctuating, the standard way of
Yes.
there you have a gap.
Yes.
But,
Here also you have a gap.
Still have a gap.
You still have a gap.
I see.
But the gap is huge. See, it's a question of who kills you first. And the answer is whatever can kill you will kill you. So if you start with a superconductor, if the gap is small, you'll destroy the gap. But if the stiffness is small, then you will never talk about killing the gap. You'll just kill the condensate by killing phase coherence. And we'll see how this is central to Kosterlitz-Thouless physics.
So you basically have a large gap.
Yes,
and
a small stiffness.
Small stiffness. And
Yes.
that is
That's what happens in a lot of strongly correlated, low density, relatively ill understood superconductors. Okay, but it doesn't happen in BCS theory. Okay, very good. So I can skip this. This is for experts. So there is such, if you open some book like Tinkham, you'll find a superfluid density. But it turns out that this separation of the stiffness into density by mass is very specific to parabolic dispersion single band systems. It's the composite object that enters all observables. But that's a technical aside. Okay, so now I want to begin telling you about my work. Okay, so this is some work that we've been pursuing over the last 5 years or so. It formed the PhD thesis of 2 of my students, Tamagna Hazra and Nishchal Verma, and also some work with my experimental colleagues Jeannie Lau and Mark Bokroth. We may not reach everything here, but let's just see how far we can go. Please don't hesitate to stop me. So the first thing we do technically is to find an upper bound on the stiffness. Okay, so first we have to write down a Hamiltonian because I'm a theorist, so we have to start with a Hamiltonian. Okay. So since I don't want to commit myself to which superconductor I'm going to describe, or I'm going to take the most general Hamiltonian you can think of. Okay, there are some bands which are completely empty, I throw them out. Some bands which are full, I don't care about them. I talk about all the bands near the chemical potential which are going to be impacted by superconductivity, the active bands. You can take an arbitrary band structure. Okay, that's the kinetic energy. And I don't want to commit myself to any interaction. I don't care whether it's phonons, electrons, Feshbach resonances, whatever. Depending on context. So I'm going to put an arbitrary interaction energy. Now, of course, if you put an arbitrary interaction energy, what am I going to do with that? The answer is I want to compute stiffness, which is the response to a vector potential, a magnetic field, for instance. So I'm going to make the assumption that the vector potential couples only to the kinetic energy and not to the interaction. So in the continuum, this is something which is minimal subtraction, P minus EA. Interactions, it won't couple to. Or on the lattice, the so-called Peierls phase factor. As you jump from one side to the other, you pick a e to the I a dot dl. So is this assumption restrictive? The answer is it's not. In fact, 99% of the systems you think of, this assumption is perfectly fine. Electron-phonon interactions, Hubbard model, TJ, density, spin, ultra-cold Fermi gases, everywhere this is fine. Then you could ask, is this assumption always valid? And the answer is no. You can certainly find examples where it's not. And here are two cases of great current interest where this assumption will not work. Okay? One is flat band superconductivity. Flat band superconductivity is when there's no kinetic energy whatsoever in the problem. We'll come back to that. But if there's no kinetic energy, I can't say the vector potential couples to it. Okay? And the second is topological bands, because it turns out that for topological bands, you cannot even write down a tight binding Hamiltonian easily. So put those aside, because those are rather special cases which are of great interest to a lot of people in condensed matter theory. But let's look at what 99.99% of the superconductors are. Let's just focus on this. We'll come back to that later if we do. Okay, so what we do is, just using positivity of spectral functions, we find an exact upper bound to the stiffness. Okay? And the upper bound, d tilde, has a simple physical meaning and much simpler to estimate than ds. So if there are any theorists in the audience, the rest can just ignore this. It's just all I've done is I've written down some Kubo formula and used a spectral representation and showed that it's positive definite. Don't worry about it, because I'm going to give you a very simple, intuitive understanding of where this comes, not where this comes from, but what this means physically. This is where it comes from. Okay, so here is the idea, intuitive idea. So I'm using an optical sum rule. I had already told you that in the optical conductivity, real part of sigma omega plotted as a function of omega, there's a delta function. And the area under the delta function is ds, the stiffness. It turns out that this object that I have used as the upper bound is, in fact, the total area under this curve. So what this bound is intuitively saying is that there is a total optical spectral weight, and what can condense into the delta function is bounded above by what is present in the whole thing. That's all it's saying intuitively. So the stiffness is bounded by the optical spectral weight. Okay, and this is purely for the experts and the theorists in the audience, that for a multi-band superconductors with arbitrary interactions, we can write down a formula for what this is, and then we can use this for calculation. The rest, don't need to worry about it.
To understand why optical conductivity is related to stiffness?
Yes, it is, but it will take me a little too far away from it. But this actually you will even find in Tinkham's book, at least for parabolic dispersion, that there is a delta. In fact, this optical sum rule for superconductors is often called the Farrell-Tinkham-Glover sum rule. Yeah, so can I duck that question because it will take me into technical territory which is not of great interest to the broader audience, but happy to tell you. Okay, good. So now, up till now I was in any dimensions, but now I'm going to focus on 2 dimensions until further notice. Yes?
The phase in the order parameter, is it a function of spatial coordinates?
It can be, and you will see that it is in the next slide. Usually you think that if you have a piece of superconductor at very low temperatures, then the phase is uniform. It is, okay? But because of fluctuations, it can be and will be in the next slide. So please wait. That's yeah, I couldn't have asked for a better question. There, you see the phase is varying in space, okay? Because I'm drawing, these arrows are the phase of the superconducting order parameter. So now here are Berezinski, Kosterlitz, and Thouless. So they showed, I mean, this is a celebrated work for which Kosterlitz and Thouless won the Nobel Prize. Berezinski passed away many, many years before that. So, okay, that the transition from the superconducting to the normal state in 2 dimensions, so that's why I emphasize 2, comes from the unbinding of vortex-anti-vortex pairs. That's the physics of the Kosterlitz-Thouless transition. So it's phase disorder that drives the transition. Okay, and it's determined by the balance of the entropy of vortex-anti-vortex pairs and the energy of creating them. So the entropy gives you a temperature term, and the energy gives you the stiffness because you have to wind the phase to get this, so the stiffness enters. So it's the balance between Tc and the stiffness that determines Tc. So in fact, what was shown in this beautiful paper is that the stiffness in Kosterlitz-Thouless theory has a jump discontinuity at Tc. So it jumps to 0 about Tc where you no longer have stiffness. This is the Kosterlitz-Thouless Tc. And there is a universal relationship between Tc and the stiffness just below Tc, or the magnitude of this jump. By universal, I mean that using renormalization group, Nelson and Kosterlitz showed that this pi over 2 is universal, independent of all microscopic details. And we're going to exploit this to the hilt. So here's the process. Tc is related to the stiffness just below Tc, Berezinski-Kosterlitz-Thouless. The stiffness just below Tc is bounded by the optical spectral weight, because the optical spectral weight told you how large ds can be. Okay, so we find an exact result independent of pairing mechanism or strength, making no mean field theory approximations whatsoever. Okay, so here is the bound on Tc, but it doesn't necessarily look very promising because there's Tc here and there's Tc on this side too. So in the remaining part of the talk, I will try to convince you that this bound is actually extremely useful, precisely when the conventional BCS theory fails. And conversely, this is an exact result. When BCS theory works, this bound is still valid, but of not much use because it's a gross overestimate. Okay? So here goes. So actually what I would have done had I had a seminar, I would have taken you from simple parabolic bands to very complicated band structures and show you how this bound works. That would bore you because you're not all condensed matter people. Let me take a few examples, and I'd be happy to discuss quantum Monte Carlo and monolera and selenide and so on with anyone who wants to discuss it. So this is what in America people often call the spherical cow. Okay, I don't know in India whether that's a good thing to say or not. Okay. So parabolic band in 2 dimensions, the simplest example you can take. Let's ask what happens to that, and you can put in arbitrary interactions that lead to superconductivity. Okay? So you have a dispersion, which is k squared over 2m, a density n, which leads to a Fermi energy n over n. And our result says that no matter what you do, the transition temperature of a parabolic band in 2 dimensions can never exceed 1/8 epsilon Fermi. It's just simple algebra to plug it through here. So you can put this here, and of course your mine too, first instinct is to declare victory, okay, saying you can never go above this line, but that's stretching things a bit because not many things here are parabolic, nor are they 2-dimensional. But, okay, as with any simple things, like if you learn in Ashcroft and Mermin, the Druder model, it tells you roughly what can happen, even though in detail you must be very wary of using it in a realistic situation. It roughly tells you that you understand why you can never exceed this, because in a parabolic band you just cannot exceed it, okay, in 2 dimensions. Then you can ask, can I test this prediction in an experiment for a parabolic band? So when we wrote this paper first in 2019, I thought the first place we would see it would be in cold atoms, okay? Because there you have parabolic bands and you have this famous BCS-BEC crossover, so that if you start with 2 flavors of fermions, you can call them spin up, spin down. Here they're red and blue. Then with very weak attraction, you form these huge Cooper pairs, and that's the BCS limit. But on the other hand, if the attraction was the largest energy scale in the problem, then you form tiny Cooper pairs, and these are just point bosons, more or less. And the ground state of this would be a Bose-Einstein condensate of these diatomic molecules. The size is much larger than the average spacing between fermions. And the beauty of cold atoms is that you have something in the lab called the Feshbach resonance, and Saptarshi and Sanyukta can show you Feshbach resonances in their labs, where you can really go from one limit to the other. And this has all been done experimentally in very beautiful experiments. And so the strongly interacting regime where the pair size for the interparticle spacing is right in the middle. In 3 dimensions, it's called the unitary Fermi gas. So I thought this, in the 2-dimensional version of this, we would see our bound. So let me draw this picture, and you can forget about all the math. Just focus on the picture. This is temperature in units of the Fermi temperature, and this is actually 1 over kFc naught, but this is weak attraction, strong attraction. So you know the answer here is BCS theory. And BCS theory tells you TC should keep on going up as you increase the attraction, because the pairs are getting more and more and more strongly bound. But the actual TC doesn't do that. The only thing you know is what the actual TC does in the BEC limit, where it must go to 0, because you can ask your students in an exam that if you have a 2D non-interacting Bose gas, then its TC must go to 0, but it goes to 0 extraordinarily slowly. Okay, this is just a guess. No one has calculated this, so it can be calculated in quantum Monte Carlo and can be probed in experiments. And here is our bound. So we think that the bound should be quite reasonably close to being saturated in the very strongly correlated regime. But this experiment is yet to be done. But fortunately for us, 2 years after our first paper, there was this very beautiful experiment from the Iwasa group in Tokyo. So they took this horrible, see, this is, people outside of condensed matter physics can never understand how anybody would even think of looking at this material. This looks horrible, yeah? Lithium, dope, zirconium, nitrochloride. But actually, its band structure is very nice and parabolic. Its density of states is completely flat with a jump discontinuity. So parabolic dispersion, 2D density of states. Now, what was Iwasa's idea? Iwasa's idea was that in the cold atoms world, you have this Feshbach resonance, you can tune the attraction. In the solid state, attraction is God-given. You cannot do anything to change the attraction. But maybe you only need to change delta divided by epsilon Fermi. So maybe you can change epsilon Fermi, but you can't change epsilon Fermi in a metal either. So he took this lightly doped semiconductor and he tuned epsilon Fermi. So he controlled delta or epsilon Fermi by tuning the density using both lithium intercalation and ionic liquid gating. And he raised TC, and lo and behold, he was actually, this is a remarkable experiment because he changes the Fermi temperature by 2 orders of magnitude, and he is never able to cross the 1/8 line. He just comes and saturates on the 1/8 line. So we were definitely thrilled when we saw this paper. Okay, so you try to go across the BCS to BEC crossover. Actually, they've never gone to the BEC side, but in the strongly interacting regime, they find that the TF/8 bound is saturated for parabolic materials. Okay, now let's move on to non-parabolic band structures. So this is some, you can do all kinds of mathematical physics using triangle inequalities, Cauchy-Schwarz inequalities, and get rigorous bounds which, of various sorts, which you can test against data. So I don't want to bore you with technical details, but probably let's just jump to a problem of great current interest, that if you take 2 sheets of graphene and twist them at just this magic angle, then somehow you are managing to get extremely narrow bands. And when in this narrow bands, you get correlation-induced insulators, where band theory would have said it would be a metal, and near those correlated insulators, you get superconducting domes. And by now, in the last 5 years, there's been a huge amount of work on understanding or experimentally probing superconductivity here. Theoretically, the question is still quite open. So we could ask, okay, and people have no idea what the pairing mechanism is, okay? Is it phonons? Is it electron-electron interactions? These are fights which will go on for decades, as they often do, okay? But we are agnostic about the mechanism. So what can we say? So if we take the band structure of twisted bilayer graphene, then the rigorous bound, which I just zoomed through, will tell us that this band structure can never support superconductivity of greater than 48 Kelvin. And if we make some approximations, we can say it can never support, so that's why I put a tilde, because it's an approximate result, more than 6 Kelvin. The observed highest TC is around 3 Kelvin. However, the assumption that I made that the interactions do not couple to the vector potential may be questionable here, okay? And I want to discuss why so. But one thing that led people to think about flat bands and topological bands is you know, the bandwidth here, which in conventional materials is like electron volts, is like 10 milli-electron volts. It's orders of magnitude smaller. So you can ask the question, what happens if the bandwidth goes to 0? Okay, because it's a theorist's way of trying to solve a very hard problem. Okay, so let's discuss 2D flat bands. So flat bands are very strange, okay, because you have no kinetic energy. If you have no kinetic energies, your electrons cannot move. If your electrons cannot move, then you ask yourself, how can you even get conductivity, let alone superconductivity? It seems like a absolutely stupid question to ask, okay? But in nature, it seems like you are getting superconductivity in very, very flat bands. So it's a good question to ask, okay? Yes?
I think I've missed what you mean by a flat band.
Okay, so by a flat band, I mean one whose bandwidth is 0. So there's no kinetic and there's no C dagger C term in the Hamiltonian. The only terms are C dagger, C, C, or some interaction terms. Yeah. So another flat band situation is the quantum Hall effect. So that's a very different situation where the bands become flat because Landau levels and in large magnetic field, and now there's no kinetic energy at all. It's quenched in the lowest Landau level. Fractal quantum Hall effect. But here it's not because of any magnetic fields or anything. It's the weirdness of the twisting to just the right amount that really flattens the band. And now as a theorist, I'm saying it's flattened so much that it's boom, none. Yeah, that's the kind of question we are asking. So there's been, and I'll explain to you what's behind it. How can you get conductivity and superconductivity? We'll come to that. So there's been important progress in the story based on mean field theory, which precedes actually twisted bilayer graphene, and all kinds of seemingly strange things appear. The stiffness scales like the trace of the quantum metric, whatever that is. I'll try to explain what that is. Okay? So of course, our question was, should we trust mean field theories when interactions are infinitely larger than the bandwidth? And more importantly, rather than doing mean field theory, can we find exact bounds without making mean field approximations of the kind that I've been talking about? Okay, so to even understand what some of the issues are, I'll have to do a quick review of geometry of band states. So you all know band electrons have block wave functions. Yes?
I have a conceptual question about
Yes.
flat band. So, from the perspective of uncertainties, so
Yes.
if you are saying it's absolutely flat,
Yes.
so which quantity is now totally indeterministic? Because you are putting a bound on the energy spread.
I'm just saying that there is no dispersion. Single electrons cannot hop. So don't think of it the way you are thinking. Just say that their single electrons cannot move.
This I understand, but some conjugate quantity somewhere must be.
So something will happen, but the interactions have to do everything. So just hold on to that thought. It is strange.
Yes.
Yeah. Okay. So what happens is, okay, band electrons are described by block wave functions. And if you take the Fourier transforms, you get something in real space which are called Vanya functions. And they form the basis states for doing tight binding and so on. Roughly speaking, the Vanya functions are like atomic orbitals, but they are localized around lattice sites. That's like atomic orbitals, but they differ from atomic orbitals because they're orthogonal between sites. They also oscillate in ways so that Vanya function here and Vanya function there are orthogonal. Now, there's some ambiguity in defining Vanya functions. So what you want to construct are maximally localized Vanya functions. That gives you the best tight binding description, which is to say minimize the R squared expectation value, or the variance of R squared in the Vanya function. That's a very natural thing to do. And that's the famous work of Marzari and Vanderbilt. And now comes this idea of quantum geometry. Okay, how small can you make the spread? Because you might think, based on elementary solid-state physics, that you can make this a delta function, or something like that. What prevents you from doing that? And the answer is something about the geometry, quantum geometry prevents you from doing that. Okay, so how to talk about that? So if I have two states, one at momentum k and another at momentum k plus dk, I can define a distance between them in Hilbert space. This is not what we usually do, but I can. So that if they're identical, the distance is 0. If they're orthogonal, the distance is maximum. Okay? But since this is k and dk nearby, I can expand that out, and that gives me what is called the metric tensor. G alpha beta, dk alpha, dk beta. And it turns out that you can prove this inequality. This is old stuff, not much known, but now coming out to be very important, that the spread of the Vanya function is lower bounded by the trace of this quantum metric tensor summed over all k. Okay? So you cannot make the Vanya functions completely scrunched up because the metric tells you how much you can do that. Okay, let's skip this. Okay, so let's look at the attractive Hubbard model on some lattice called the Lieb lattice, which has a flat band. Okay, and what I'm going to do is I'm going to project my Hamiltonian onto this flat band, and I'm going to derive a low energy effective Hamiltonian. And now comes the physics of what happens in this flat band. Once I've projected down to this flat band, the interaction minus u, ni up, ni down, is so strong, it's infinitely strong compared to the bandwidth, that boom, I just form an on-site pair. Now it's not strictly on-site, it's actually in the Warnier function, but you can think of it that way. It's highly localized pair. So you get tightly bound pairs. And now these tightly bound pairs can hop. Okay? Why can they hop? Because the spread of the Warnier function allows them to hop. When you look at the so basically, you get a flat band Bose-Einstein condensate. Transport and superconductivity comes from the hopping of pairs, but there's no single particle electron hopping at all in these models. That's how flat band superconductivity develops here. Okay, and then once I have this effective low energy Hamiltonian, you can derive a low energy optical spectral weight bound. So you can just look at the spectral weight for intra-band optical transitions without worrying about inter-band physics, and that will give you a tight bound. And when you do that, you get this bounds. And let's not worry about the lower bound for want of time. Let's just look at the upper bound, because the upper bound is very physical. Low energy optical spectral weight. It depends, its dimensions are dimensions of energy. The only energy scale when you are in this flat band is the interaction, so U. It depends on the filling of this band, because if that band is completely filled or completely empty, then of course there'll be no transport, hence this N tilde. Okay? And then comes the most important piece, which is the Warnier function spread. Because if the Warnier functions were not spread, you wouldn't get, the more spread they are, the more transport you get. So that's the bound on the low energy optical spectral weight. And that gives you a stiffness bound, and that gives you a TC bound. Okay? And it's very important to note that there is no bound on TC over epsilon Fermi. Because if I had kept my chemical potential at 0, say half filling this band, or at any filling this band, then EF is 0. But I have a finite upper bound on TC, so TC over epsilon Fermi bound is infinite. Okay? But that's like saying, please don't treat this as a parabolic band. Okay? The optical spectral weight bound is completely physical and always valid. It's just not related to epsilon Fermi. You can also play this game for topological bands, and maybe I will skip this, except to tell you what is the challenge. Then let's not worry about how we met the challenge. Roughly speaking, if you have a topological flat, or you have any topological band, flat or otherwise, then the Chern number is an obstruction to obtaining exponentially localized Warnier functions that respect all symmetries. I guess the sort of very hand-wavy, intuitive way of saying is that in a topological band, the boundary knows about something inside the bulk. You can't separate it out. That's why you can't get, this very sharply localized Warnier functions. Okay, that's a very crude reason. In any case, you can play this game and also get upper bounds. But let's skip it because I want to leave more time for questions. How much time do I have? 10 minutes or 5 minutes? 5 minutes? Okay, maybe I'll skip the experimental bit too. So this is like So this paper we published earlier this year with my colleagues Jeannie Lau and Mark Bokrath, who are experimentalists, which has nonlinear transport, very strongly coupled superconductivity and superfluid stiffness. So nonlinear transport I'm definitely going to skip. But what I want to show you is that, KFC is some kind of telling you how strongly coupled the superconductivity is. In conventional superconductivity, the size of the pair is thousands of times the microscopic spacing KF inverse, okay? Here, KFC is of order 1 to 10, very tightly bound pairs, okay? And if you look at TC over EF, you can see that TC over EF is not of order 1. It can even become 5, 7, 9, because the optical spectral weight is not a bound on TC over EF, and we have a double whammy. It's a nearly flat band, as I already explained, but also the Dirac dispersion comes in the way, which I happily explained to others. Okay, this was also in this paper is the first experimental estimate of the superfluid stiffness ds in twisted bilayer graphene, and again a demonstration that the scale of stiffness is not set by the band dispersion. Okay, let me just end a little bit with this question. So if we did all of this in 2 dimensions, why don't we just use this to attack the 3-dimensional problem? Okay, and there are multiple challenges in this problem. Okay, the data seem to certainly suggest that there may well be a bound, because many of these materials, see here, these are all the cuprates, these are heavy fermions, they all lie below it, and they're all 3-dimensional materials. If you look at the data in cold atoms for the 3D unitary Fermi gas, then it turns out that experiments in quantum Monte Carlo show you that the maximum TC is 0.22 the Fermi energy, as opposed to 1/8. Okay, this is 3 dimensions. Okay, but this number we only know either from numerics or experiments or approximate calculations, such as the one shown here. You don't really know this as a bound or anything like that. Okay, so one question that you can ask, experimentalists actually always plot the BEC line in 3 dimensions and somehow feel that this is a bound, and that's not true. The one question you can ask, that we all know how to solve the Bogoliubov-Bose gas. I mean, Bogoliubov showed us how to do that in 1944, so we should know that now. Okay, so does the non-interacting BEC give an upper bound on the TC of the weakly interacting Bose gas in 3 dimensions? It's a question, right? Is the non-interacting BEC equal to the TC, less than the TC, or more than the TC? Now, it turns out this question has many wrong answers by many famous people, okay? So Feynman certainly got the sign wrong here. He argued that TC is lower. Fetter and Waleczka, which is a standard book in many-body theory, also gives the wrong answer. But it's rigorously known that for a dilute Bose gas, interactions raise TC above the BEC temperature. So the BEC temperature is not an upper bound for any TC. Okay, so that's the first thing that you might have thought of doing, and that's wrong. The second thing is there are some issues both related to universality, and I don't know how many critical phenomena or quantum critical phenomena aficionados there are here, so let me not actually get into the technical details. But both if you look at thermal phase fluctuations near a finite temperature phase transition in 3D, or if you look at quantum phase fluctuations near a 2+1D quantum critical point, it turns out that there are problems in 3 dimensions that we do not know how to address. And again, I'm very happy to discuss that with anyone who wants to know these. And this is not just all theory land. Actually, in cuprates, there's a whole series of papers, including this data by my colleague Tom Lemberger on the penetration depth of underdoped cuprates, which shows that in 3-dimensional materials, TC scales like the square root of the stiffness and not like the stiffness, which is what we thought we could have used. In 2D, it all works out. Okay, so let me just end because my time is running out, and I talked to you about superconductivity in general, upper bounds in the superconducting TC in 2D, exact results on flat band superconductivity, some experiments on magic angle twisted bilayer graphene, which I think we still don't fully understand, and open questions on bounds in 3D. So there's lots of stuff to do and some things on which we have made progress. Thank you very much.
So one question is, do we understand what physical conditions are required to saturate the bound? And
We do. I mean, not that, if you prove a bound, you don't know rigorously when it will be. But basically, it's like in very strongly interacting systems where the pair size is comparable to the interparticle spacing, we have many examples of where this bound is saturated. And I can show you some comparisons with quantum Monte Carlo, which also give a lot of insight into this story. I'd be happy to. I skipped that because, there was just too much to talk about.
yeah, so very naively you drew this optical spectral weight curve, and
Yes.
so the DC part needs to be much larger compared to the AC part, I guess. Is that one way to understand?
No, that's not quite the way to understand it. Do I
Okay.
have the? Okay, we can have this discussion offline
Sure.
about this comparison with Monte Carlo. You see, the thing is, in an experiment, you'll only see whether it works or it doesn't work.
Yeah.
But with Monte Carlo, you can get some more sense of when is it working, why is it not working, and so on. I'm happy to discuss that with you.
No, this is a very naive question. If I see that there is this gap is the kind of order parameter for these superconducting transitions.
Yes.
So so you are saying there are two parts.
Yes.
One is the amplitude part and another is the phase part.
Yes.
Now, if how this amplitude and phase is related to TC? Because I thought below some TC, this amplitude and phase should come non-zero.
Yes.
Above that TC, it should go to zero.
So the thing is, I think outside of the realm of BCS theory, thinking of the energy gap as an order parameter is a very dangerous thing to do.
Okay.
Okay, because in many sort of interesting superconductors, so for instance, the unitary Fermi gas, the BCS-BEC crossover is one example. The normal state of cuprates is another example. The normal state of highly disordered superconductors near a superconductor insulator transition is a third example. In all these examples, some kind of an energy gap, which is often called a pseudo gap, persists even above TC. So therefore, it's not a good idea to look at a spectroscopic gap. You see, in BCS theory, the word gap is used for 10 different things. It's the order parameter, it's the spectroscopic gap, it's something else. So if you just say, as for an experimentalist, how do you measure a gap? You measure it in spectroscopy, say tunneling.
Okay.
Yeah. So, or photo emission, or some other single particle spectroscopy like that.
Okay.
That is not a good idea for a superconducting order parameter. There are many examples of gaps persisting above TC.
Okay. Okay.
So maybe that's part of the confusion,
Okay.
right?
Yeah.
And so if you think from a StatMech point of view, rather than from I actually don't know what your background is, so I don't know what answer you would like. Experimental answer is good enough, or do you
Yes,
want?
experimental is good enough.
Okay, very good. Thank you.
So you partially answered this question. I was going to ask, what about disorder? Because interaction is one thing,
Yeah.
but now over the space, if you have the ground state eigenvalues, if they are
So actually, you can put disorder into this story. It's a somewhat strange circumstance that the work on giving you upper bounds in the presence of disorder was done 35 years ago in a paper that Arun Paramkanti, when he was my student, wrote with Nandini Trivedi and me. But for some reason, we never pursued this general story back then. So we know exactly how to handle disorder. It's been done. But the answer is the following. What does disorder do? Even in conventional BCS superconductors, it lowers the superfluid stiffness. Okay, so no problem. Yeah.
So again, a naive question, but back to that slide where you talked about the two possible.
Let's go
yeah.
back to that.
So what I'd like to understand is just sort of on a purely general physical perspective of what this phase. So phase correlation.
Yes.
Somehow, long range phase correlation is
Yes.
what is propping up the even if the gap is large, but there is fluctuations, if it's randomized,
Yes.
then you get no superconductor.
Yes.
But when you have long-range phase correlation,
Yes.
so, but you said it's different from having long-range interactions or
Yes.
long-range,
Yes.
and the
So-
picture you gave was elasticity. So somehow that there is a, yeah. So maybe just sort of trying to
Yeah,
understand
so
this,
no, it's a
yeah.
very good question. Elasticity, okay. So let's think of some StatMech problem, okay. So the range of correlations has absolutely nothing to do with the range of interactions. Ising model, you have nearest neighbor interactions, but you can get long range correlations as you approach TC. Yeah, so that's one thing. So the interactions are always short range here. The Coulomb interactions are not playing some major role here, okay. This screened out in a superconductor, yeah, okay. That's one thing. Now, second thing is, okay, so if you think of superconductivity as a broken global U1 symmetry, which is a good way to think about superconductivity from many perspectives, then the order parameter has an amplitude and a phase. And just as in a magnet, okay, there are two things. First, you want to form the local moment. If there's no local moment, then it cannot order. So that's the amplitude. But then if you say something is a ferromagnet, if the directions of the magnetization are oscillate or randomly oriented, you won't get a ferromagnet. For a ferromagnet, you want all the spins to align. It's the analog of that's what's happening in superconductivity. This tells you the amplitude of the order parameter, and the uniform phase or long range phase correlations tells you that you get long range order in pretty much the same way as you get in magnetism.
So essentially, it is a symmetry breaking
It is
phase,
absolute.
and it's in that sense completely analogous to the Ising model. Right?
Yes,
Yeah.
except the symmetry in the Ising model is a Z2 discrete symmetry, whereas here it's a U1 continuous symmetry. That's why you have a complex order parameter. Okay, and then the question is, in the Ising model, okay, the amplitude is just given to you, but in a superconductor, the amplitude is not given to you. First, you must form the pairs to make the amplitude, and then you must condense the pairs, or at least get algebraic order between the pairs. That's the phase coherence. Yes, please.
This is on, so that graph of DC versus Ka, the
Yes.
Fermi. So it seems like if you have higher Fermi energy, you have higher TC.
You can have higher TC. You don't necessarily have higher TC. Look at aluminum. Its Fermi energy is huge, but its TC is quite low.
Okay.
You can have, because we say this is the bound in 2 dimensions at least, or some bound like this.
Okay. So, I mean, what physically this Fermi energy is telling about that superconducting transition?
So the thing is, normally the Fermi, at least in BCS superconductors, the Fermi energy is orders of magnitude larger than TC. Why? Because TC is determined by a very weak, attractive electron-phonon interaction.
Okay.
Okay,
Yeah.
Fermi energy for aluminum is 1000, 10,000 Kelvin, but TC is 1.17 Kelvins.
Okay.
It doesn't mean aluminum is boring, by the way. Okay, all these superconducting qubits are made of aluminum. I don't want to run down aluminum. Okay, so that's what it is. But the hard, so then BCS theory works fantastically here. So we don't worry about all these systems here. But this is completely outside the purview of, because you see, if you only distort a little, like if you only destroy the Fermi surface just near the Fermi surface, that's BCS theory, weak attraction. But if TCs are comparable to the Fermi energy, the whole Fermi C is completely rearranged. That means you have some very strong interaction. But it's not easy to get there, but in some materials you do get there, like magic angle twisted bilateral. So, in Kelvin, it's not that this is such a large temperature, okay, or here also, or actually this is an important point. So let's see this other graph which shows cold atoms. What I didn't tell you is that these cold atoms are multiplied by 10 to the power 8. So the cold atoms are actually down in the basement. But they're still on this line. Okay, why are they so down in the basement? Because they are so dilute that their Fermi energy is very tiny. Okay.
So this experiment you showed where they decrease this Fermi energy.
Yes.
So by what mechanism they decrease it?
Okay, so that is actually a tour de force. Because in a metal you can't change the Fermi energy.
Yeah, so it's pretty robust, right?
Yeah. So here. So what they do, or here, what they do is they do two things. First of all, they put intercalation. Okay, so the lithium ions then give up or some electrons to the system. That's one way of adding electrons to the system. And the other is something called ionic liquid gating. I don't know if you know about that. It goes back to Helmholtz, this idea. What you do is you make a capacitor and you put a huge electric field across it, which you cannot do with ordinary dielectrics. Now, if you have a parallel plate capacitor in which you put a huge electric field, then you can imagine that you can change the charge density by a huge amount, but you shouldn't put so large that you burn out your capacitor. Okay? So these are the two tricks that they used. And the reason why they could do it is because this actually, zirconium nitrochloride is actually almost a band insulator. So you can just populate this band with electrons, and then you can change the Fermi temperature or the density by 2 orders of magnitude. So you're doping a band insulator partly chemically and partly through electrostatic gating.
And if you want to go along this, you have to change the material, or like for a fix that you cannot.
I mean, if we knew how to increase the TC of a system, we would be all rich and famous, right?
No, I mean what you're saying is it's just easier to go along.
No, I'm just saying, okay, in the cold atoms, actually, everything is down here, but they know how to change the interaction. In a solid state, we can't change the attraction between electrons. That's not possible. We can only change the density and hope that something interesting happens, and something interesting did happen. Yeah. Okay. Yeah, one more question.
In cold atom,
Yes.
how is the interaction taking place? Like, is it boson
So then you need to understand the Feshbach resonance. Okay, I'm not going to try to give you a one-line argument of this Feshbach resonance. I can point you to the literature where you can find either very hand-wavy discussions, or you can find very detailed mathematical discussions. Or you can ask Saptarshi, he'll show you, or maybe Sayukta also. They have in their lab, the ability to change this interaction. They can show you the apparatus by which they actually change a magnetic field.
We use magnetic field to change the interaction between the atoms. So we use magnetic field to change the interaction between the atoms, and so you can go to a very high scattering length from very large negative scattering length to very large positive scattering length using this. So the exact mechanism, it's a long discussion.
Yeah, I mean, I don't even know whether you know what scattering length is. And okay, so good. So next time they teach you scattering theory in quantum mechanics, you have to pay attention, and you have to understand what it means to have a negative scattering length or a positive scattering length. Phase shifts. So you have to learn the method of partial waves. Okay, good. But okay, I'll happily tell you. I'm joking. I'm giving you a joking answer, but I'll happily tell you afterwards. Yeah?
So let's thank
Oh, thank you very much. Thank you very much.
And we have tea. There
Okay.
We have more questions discussion.
Oh, this is wonderful. I should get rid of this.